The last sunrise does not arrive with ashing violence. It comes slowly, like a tide of fire trying to remember the shape of the sky. The air is thin. The oceans boil at their edges. Shadows lose their meaning as the horizon swells with a red glare that climbs higher than any mountain ever carved by plate and time. Nothing screams. Nothing rushes. The sun rises into its giant form with a patience that feels cruel, and the world below waits as though stunned by the weight of a star's final intention. That vision is not myth. It is not prophecy. It is the end written into a process so strange that classical physics once insisted it should barely function. A star, built on improbable interactions, has held us steady for billions of years. It has drawn rivers across stone, pushed forests toward the sky, and filled every living cell with energy from collisions that almost never succeed. The paradox tightens. The sun appears stable because human time is short. We look at its brightness and see constancy, yet its calm face hides a depth of motion that never stops, a core densifying with age, a reservoir of fuel thinning in slow spirals, magnetic structures that twist and snap like wires pulled too tight, a future that is not static but already underway. Step back and consider the light itself. Every ray warming your cheek began as a trapped wanderer, deep inside the star. Photons collide with particles that crowd so thickly that each step forward becomes a stumble. They scatter for hundreds of thousands of years. They climb through layers that act like different worlds, each with its own rules. Only when they reach the thin outer shell do they break free, crossing space to reach Earth in minutes. By the time a beam reaches your hand, humanity has changed languages, tools, and landscapes. That warmth is a message from a past so distant it stretches beyond memory. How can such an ancient messenger tell us anything about the future the sun is building? Look again at the daylight. It is not a simple glow. It is the summation of improbable successes. Most protons inside the core collide billions of times without merging. They fail. They rebound. They wait for quantum chance to let them slip through their own mutual repulsion. When one pair succeeds, the reaction spreads energy in ripples. That energy pushes outward, shaping the star's pressure and size. The whole star is a negotiation between gravity that wants collapse and fusion that resists it. As long as balance holds, the sun shines. But balance is not immortal. The core thickens with helium ash. The burning shell migrates outward. A sequence long in motion begins to tighten its path toward transformation. Why should a star that thrives on chance be so reliable across such enormous spans of time? Why does the engine that allows only the faintest probability of fusion per collision manage to power entire oceans of life? And if stability depends on such fragile statistics, what happens when those statistics shift beyond their limits? At dusk, you cannot see the inner regions where these arguments unfold, but instruments orbiting Earth can. They record tremors that shake the sun like a drum skin. They map sound waves that pass through its interior, revealing hidden layers. In these patterns lies evidence that the star's fuel is gradually rearranging itself. Helium contracts the core. The surrounding plasma adjusts its flows. Even if the surface looks unchanged, the interior is preparing for a state it has never reached before. That transition will come with slow inevitability. The star will expand. Its outer layers will cool and redden. Its radius will stretch past the orbit of Mercury, then Venus. Whether Earth survives long enough to be engulfed or is baked barren before contact, the result is the same. The sun's aging will erase the familiar world. Imagine walking across a silent field. A gentle wind moves the grass. Clouds drift in slow columns. Nothing in the scene suggests danger. Yet above you is the engine that will one day strip the sky of its blue. It is a strange experience to stand under so much brightness and realize it is temporary. Every creature that ever lived has done so under borrowed conditions. Every breath you take is part of a story that will end with heat rather than cold. The cosmos does not promise permanence. It promises motion and change. This knowledge is not meant to frighten. It is meant to anchor. The sun's fate is not an abrupt extinction, but a slow reconfiguration, a transformation visible only on scales far beyond human lifetimes. We know this because we have seen other stars change. Some swell quickly. Some drift through long stages of expansion. Their brightness curves map the life cycles that ours will follow. Their structures reveal the physics that govern aging stars. When placed together, these observations form a map of inevitabilities. Our star is just one point on that map. The mystery deepens when you consider the sun's place in the galaxy. It is not stationary. It travels through a river of stars, and over immense timescales, other suns drift close enough to bend the orbits of planets. A passing red dwarf may tug at far-flung regions of our system. A more massive star could perturb distant comets. With enough time, even Earth's orbit is not immune to subtle shifts. The future we imagine, with Earth simply waiting for the red giant phase, is not guaranteed. The sky that seems calm is part of a crowded environment where small gravitational whispers accumulate into long-term consequences. What looks like cosmic stillness is a slow dance with unseen partners. Consider what this means for the familiar sunrise you see each day. The circle of light emerging from the shadowed horizon is not merely a daily event. It is the visible edge of a process older than continents. It is the surface glow of a star held in balance by forces that will eventually fail. But inside that glow is the record of everything the sun has ever done for Earth. It forged the heat that drove weather patterns. It shaped the chemistry of early oceans. It coaxed life to expand and adapt. All of human history is a brief companion to a star whose lifespan stretches across epochs. You can stand outside now, raise your head, and feel the sunlight touch you. That touch is real and immediate. But the physics that created it began long before the first mammals appeared. The warmth carries a history that predates the very ground you stand on. And in that history lies the blueprint of the future. Once the core accumulates enough helium, its equilibrium shifts. Fusion moves outward. The sun swells. Its surface cools to a deep red glow. Its brightness increases. Tides on Earth intensify. Atmosphere leaks away. Eventually, the expanding star either grazes or consumes the world that nurtured us. That sequence has happened countless times across the galaxy. It will happen here. The question is not whether the sun will change, but what that change means for us. What does it mean to live in the middle of a process moving so slowly it becomes invisible? What does it mean for a civilization to understand its star deeply enough to foresee its end, yet remain bound to the very energy that will someday remove its home? It is possible to trace answers in the subtle details. Solar vibrations detected by instruments, magnetic fields that coil and snap, patterns in the cycle of sunspots, light curves mapped by telescopes at extreme ultraviolet wavelengths. Each piece is a clue. Together they whisper the same direction. The sun is shifting. Its future is measurable. Its transformation is certain. The paradox grows sharper with every revelation. A star that should barely shine powers all of life. A star so constant that ancient civilizations worshipped it is slowly becoming something very different. A star whose surface appears calm can unleash storms that interfere with satellites, grids, and navigation. A star whose gravity shapes the orbits of planets is itself shaped by the passage of other stars. When you place all these layers together, the sun is no longer a familiar disk in the sky. It becomes a complex engine headed toward an ending we cannot stop but can understand. Understanding is the beginning. From here, the journey will take us into the machinery beneath the sun's surface, into the improbable quantum reactions that keep it burning, into the storms that ripple across its outer layers, and into the galaxy that wraps around it like a shifting sea. The deeper we travel, the clearer the finale becomes. The last sunrise is not a distant story. It is a slow truth unfolding moment by moment. As we follow these threads inward and outward, from the core to distant stars, A larger picture emerges. The sun is preparing for a future shaped by both its own physics and its motion through the galaxy. We stand on Earth, watching a star that appears calm, yet carries within it the seeds of its transformation. Everything we will explore in the next act rises from this paradox. The sun is gentle enough to nurture life and powerful enough to erase it. Between those two realities lies the path we must navigate. If this cosmic journey speaks to you, tap like and subscribe to the Quiet Universe channel. The sun looks simple from a distance. A smooth disk, a familiar glow, a steady rhythm rising and falling across the sky. Yet the calm surface hides a structure so layered and volatile that even our best intuition falters. This chapter begins where the light begins, deep inside a chamber we cannot see, where matter behaves like a crowded city whose residents never stop moving. The outer calm is an illusion built on structures stacked with precision, each layer shaping the energy that struggles to escape. What appears as a uniform ball of fire is instead a labyrinth of forces that rarely reach harmony for long. Imagine descending through the golden haze, sinking past the reach of sunlight. The first boundary you cross is the photosphere, a surface that is not truly solid but acts like a frontier where light gains the freedom to leap into space. Beneath it lies a zone of turmoil. Cells of plasma rise and fall in slow, roiling patterns, like continents of liquid metal flipping themselves over. These cells transport heat with the indifference of a tide. They churn upward until they cool, then collapse back into the depths. This motion shapes the granulation pattern seen in telescopes. It is the visible signature of the sun's restless interior. Continue deeper, and the behavior of matter changes. The density climbs. The pressure grows. The chaos of convection gives way to a region where photons do the heavy lifting. They collide with electrons and ions again and again. Their path becomes jagged, crooked, slow. In this radiative zone, light loses its freedom. It moves more like an idea slipping through a crowded hall than a beam racing through space. Each interaction deflects it. Each deflection adds delay. Only after hundreds of thousands of years does a single packet of energy approach the upper layers. When you feel sunlight on your arm, you are feeling the end of a journey that began long before humanity learned to farm or speak. This picture grows stranger as you approach the core. Here, the plasma is compressed to such extremes that atoms hardly behave as separate entities. Temperatures rise to millions of degrees. Pressure reaches levels Earth will never experience. Protons collide with relentless frequency. Yet almost all of these collisions fail to fuse because the electric repulsion between protons works against them. Classical physics would leave the core cold, and yet it burns. The explanation lies in the quantum rules that allow particles to slip through barriers they should not cross. Think of it like this. The protons act as though they borrow the possibility of being close enough to merge even when they lack the energy to force the issue. This slim chance, repeated across a vast crowd of particles, becomes the engine of the sun. The core is not a roaring furnace. It is a controlled negotiation between probability and pressure. When protons fuse, the resulting helium nucleus is slightly lighter than the ingredients that formed it. The missing mass becomes energy. That energy tries to escape. Pushing outward on the layers above, the outward pressure stabilizes the star against the crushing pull of gravity. In this balance lies the long period of relative calm we experience on Earth. Gravity tries to collapse the sun. Fusion pushes back. The star becomes a self-regulating structure that adjusts when either side gains an advantage. If fusion increases slightly, the star expands a little, reducing the pressure and slowing the reactions. If fusion decreases, the star contracts slightly, raising pressure and restoring the burn. This delicate feedback keeps the sun stable across billions of years, but it is not eternal. Every minute, helium collects in the core. It is the ash of fusion. It does not burn easily at first. It accumulates. It sinks. It changes the density profile of the interior over immense stretches of time. This buildup alters how energy moves through the layers. The sun we see today is already different from the sun that first illuminated Earth, and the one that will exist billions of years from now will be different still. Inside this gradual evolution lie the seeds of the catastrophic expansion that will come later. Our instruments confirm that the sun is not a uniform sphere. Vibrations run through it like seismic waves through Earth. They ring the star with subtle patterns that reveal hidden features. Scientists read these oscillations as clues to the interior. Peaks in the frequency spectrum correspond to particular layers. Amplitudes reveal shifts in density. By mapping these signatures, we can reconstruct the structure beneath the surface. We can detect the depth of the convection zone. We can estimate the speed at which energy travels upward. We can trace how the core grows more compact over time. What does this mean for us today? It means that beneath the familiar glow is a system forever adjusting itself. Each adjustment carries implications for how the sun behaves at its surface. Magnetic fields emerge from these internal flows. They twist and anchor themselves in patterns we observe as sunspots. They connect to loops that snap in solar flares. The calm star at noon is shaped by forces that began deep underground. The next solar storm may be seeded by currents moving near the core. The quiet periods may reflect subtle shifts in energy transport between layers. You can picture the sun's interior as a multi-level factory. Some floors run on steady routines. Others push heavy machinery. Others handle delicate operations that must avoid overload. If one floor changes pace, the rest must adapt. This metaphor captures the essence of the star. Layers communicate not through spoken signals but through physics. Pressures equalize, temperatures drift, magnetic fields thread through the entire structure. Nothing acts alone. Everything depends on everything else. Occasionally, we see the consequences of this interconnectedness. A slight change in internal flow may lead to variations in the number of sunspots. Those variations alter the frequency of storms. Storms influence the environment around Earth. They disturb satellites. They shift auroral patterns. Life on Earth feels the distant consequences of motions occurring deep inside a star we cannot touch. That is the scale on which we exist. A scale where invisible processes ripple outward until they shape daily experience. Why should this matter to us if the sun remains mostly stable? The answer lies in the long view. Stability today does not guarantee stability forever. The same patterns that keep the sun in balance also guide its aging. As helium accumulates in the core, the balance shifts. Fusion occurs in a shell surrounding the central region. That shell migrates outward. The outer layers respond by expanding. When the star enlarges enough, the conditions for fusion change again. The cycle repeats with new parameters. Eventually, the sun will leave the long stretch of its main sequence life and enter a broader state where expansion becomes unstoppable. Earth sits near the path of that future growth. The deeper we study the sun's interior, the more clearly we can map its timeline. We can estimate how much fuel remains in the core. We can track the rate of helium accumulation. We can observe the subtle changes in oscillation patterns that mark transitions in internal structure. These measurements let us project the long arc of the sun's future. They let us understand when the gentle balance will tilt. For now, the sun remains stable. Its energy output varies only slightly. Its surface patterns follow cycles. But beneath the surface, the slow processes that govern its fate continue without pause. Each day, the core grows a little heavier. Each day, the outer layers feel the faint push of heat redistributed from within. Nothing dramatic happens on human timescales, but everything is changing beneath the stillness. There is a deeper insight buried here. The sun we think we know is not the sun that truly exists. The familiar disk in the sky is only the final surface of a vast internal unfolding. It is the end point of energy created far below. It is the final chapter of a story written beneath millions of kilometers of plasma. If we could witness this story from within, we would see a dynamic world with currents, pressures, and collisions beyond any terrestrial comparison. A world where light struggles, where particles merge by improbable chance, where equilibrium is temporary, and where time itself shapes the future of planets. That hidden story frames everything we will examine in the next chapter. where the sun's improbable engine rises to the foreground. The deeper you descend into the sun, the more familiar physics begins to feel inadequate. Heat and pressure rise until atoms lose their identities. Protons drift in a haze where distance becomes uncertain, and collisions happen with relentless frequency. Yet almost all of those collisions fail to fuse. The barrier between protons, the electric repulsion that keeps them apart, is immense. Classical physics would predict a cold, dark core. It would insist that two positively charged particles should never merge in numbers sufficient to warm a world. And yet the sun shines. Something unexpected is at work. Something that defies intuition. A quantum mechanism that makes the impossible happen often enough to light an entire system. Picture the core not as a furnace, but as a crowded hall where particles move with frantic urgency. They jostle, they ricochet, they form temporary alignments. Temperature describes the collective energy of this chaos. Pressure describes how tightly the crowd is packed, but neither temperature nor pressure alone can force protons to merge. They lack the classical energy required to leap over their mutual repulsion. Even at millions of degrees, the gap is too wide. Fusion should not ignite. And yet, through an avenue that exists only in the probabilistic landscape of the quantum world, it does. The key lies in tunneling, a phenomenon that allows particles to slip through barriers they do not have enough energy to climb. Think of it like this: rather than jumping over a wall, a proton sometimes behaves as if it briefly occupies a region on the other side of the wall. The effect is rare. If you could watch each collision, you would see billions of failures for each success. But the core contains so many particles, and collisions happen so often that even an improbable pathway becomes significant. When a successful event occurs, two protons merge into a configuration where one transforms into a neutron, forming a fragile new nucleus. This first fusion step is slow, but it initiates a chain that heats the star. The chain continues through several phases. Newly formed nuclei combine with other protons, slowly building helium. Each step releases energy. That energy ripples outward, adding heat, adjusting pressure, and maintaining the delicate counterbalance against gravity. Over time, helium ash accumulates because it is heavier and settles inward. The fusion process is not just a producer of light, it is a sculptor, shaping the internal architecture of the star through the slow accumulation of its own byproducts. What makes this engine extraordinary is how self-regulating it is. If fusion rates increase, the core warms slightly. The added heat causes the inner region to expand. Expansion reduces the density. The reduced density lowers the rate of collisions. The fusion rate drops back down. If fusion slows too much, the core contracts, increasing density and temperature, raising the reaction rate. The sun maintains this balance not through intention but through the natural interaction of heat and gravity. It is a dynamic equilibrium that has held for billions of years, yet it relies on quantum events that are statistically unlikely. Consider the scale of improbability. For every fusion event that succeeds, countless collisions fail. If the universe were only a bit different, if quantum rules did not allow tunneling, or if the strength of electric repulsion between protons were slightly higher, stars like the sun might never have ignited. Darkness would have dominated. The elements we rely on would not exist. Life as we know it would have been impossible. The sun's brilliance depends on a razor-thin balance between classical barriers and quantum permissions. This balance is not guaranteed in all possible universes. It is a specific result of the laws that govern ours. To understand the engine fully, imagine how the energy released by fusion travels. It does not move outward cleanly. Photons emerge from reactions and immediately collide with neighbors. They lose direction. They scatter in all possible paths. The radiative zone that surrounds the core acts like an obstacle course where photons advance only small increments before being thrown off track. This slow movement spreads heat evenly, creating a temperate boundary between the chaotic core and the turbulent convection zone above. It also ensures that any sudden surge in energy becomes smoothed out before reaching the surface. The The sun's stability depends on this long diffusion time. Above the radiative zone, structural changes occur as heat becomes transported by motion instead of radiation. The convection zone churns constantly, carrying packets of energy upward in giant columns of rising plasma. This movement shapes the surface granulation pattern and helps structure magnetic fields. But the source of the energy remains the quantum events in the core. Every ripple across the surface, every loop of magnetism, every solar flare begins with the improbable fusion of two protons. What makes this engine even stranger is how quietly it operates. There is no central inferno roaring with sound. Sound cannot travel in a vacuum, and the density variations inside the sun dampen any familiar echoes. Instead, the star vibrates in patterns scientists detect through subtle oscillations. These patterns reveal the structure of the inner layers. They allow us to infer the temperature distribution and the shifting boundaries of the fusion region. Through this technique, we can listen to the sun without hearing it. The quantum engine is not a constant machine. It evolves. As helium accumulates in the core, the internal density profile changes. Temperatures rise because helium compresses under gravity more tightly than hydrogen. The fusion zone migrates outward. Over time, the balance between pressure and gravity shifts. The sun brightens slowly as the core warms. This gradual brightening has shaped Earth's climate over billions of years. It will continue to shape the environment until conditions become unsuitable for life, long before the sun reaches its giant phase. Why does this matter for us? Because the sun's energy output is not fixed. It increases over time. Before the future expansion toward a red giant shape, Earth will experience a rise in solar luminosity that affects climate, oceans, and long-term habitability. While the star remains in the main sequence phase, the warming is slow enough that planetary systems and geological cycles can absorb the change. But eventually the increase becomes pronounced. The inner edge of the habitable zone drifts outward. Earth moves toward a regime where maintaining surface water becomes increasingly difficult. The processes in the core, invisible to us, guide the long-range trajectory of life on our planet. If you look at the sun through instruments that measure neutrinos, particles created directly in fusion reactions, you can see the inner engine in real time. Neutrinos escape the sun almost immediately. They provide a direct line to the core. Measurements match theoretical predictions, confirming that fusion proceeds as models suggest. This agreement affirms our understanding of the quantum steps involved. It validates the picture of a star whose internal engine is governed by improbable but steady events. Through these measurements, we can trust the long-term models that guide our predictions about the sun's future. This picture is not static. New observations continue to refine our understanding. Upcoming missions and ground-based telescopes may reveal more about how the quantum engine interacts with magnetic phenomena near the core. There are open questions about how flows in the radiative zone influence surface cycles. There are debates about subtle effects that could shift long-term predictions. But the broad outline remains firm. The sun burns through a series of improbable steps that collectively produce a steady output of energy. And those steps will eventually lead to profound changes in the star's overall behavior. The improbable nature of tunneling is more than a technical detail. It is a reminder that the sun does not operate according to everyday expectations. It follows rules that only make sense at the smallest scales. These rules enable the stability that shapes our world. They allow fusion to proceed in a gentle, sustained fashion rather than erupting in violent bursts. They dictate the pace at which the sun ages. They set the timeline for its expansion and eventual transformation. They shape the path Earth will follow. As we move forward, the next stage of our journey will carry us from this improbable engine to the storms that brew on the sun's surface. The sun looks calm from a distance. Its face is smooth to the eye. Its brightness barely shifts from day to day. The disk that rises each morning seems composed of pure steadiness. Yet this calm is only a surface impression. Beneath the soft gold lies a world of eruptions, magnetic knots, and sudden releases of energy. The same star that warms Earth with gentle light can unleash storms powerful enough to disrupt satellites, overwhelm electrical grids, and alter the upper atmosphere. A quiet sun is never entirely quiet. It is a place where tension coiled deep within magnetic fields can break without warning. To understand these storms, imagine looking at the sun through wavelengths invisible to human eyes. The flat disk becomes a landscape of arcs, loops, and twisting filaments. Magnetic structures rise from the surface like luminous ropes. They sometimes stabilize for hours or days, then reorganize themselves with surprising speed. The plasma that fills these structures obeys magnetic lines, more than gravity. When field lines wrap around each other, energy builds. When they snap into simpler configurations, the release is violent. A solar flare begins with that snapping. It is not a fire. It is a sudden rearrangement of magnetic fields that accelerates particles to high energies. These particles travel along the lines that shape the sun's atmosphere, heating plasma until it shines intensely in ultraviolet and X-ray wavelengths. The surface brightens locally. Radiation spreads through space. If Earth happens to lie in the path, the upper atmosphere reacts. Ionization levels rise. Radio signals become distorted. The calm star has disrupted the quiet of a world far away. But flares are only part of the story. Sometimes the magnetic reconfiguration is strong enough to launch a bubble of charged particles into space. This is a coronal mass ejection, often called a CME. The sun expels a massive cloud of plasma, carrying billions of tons of material outward. The cloud moves through the solar system, shaped by its own magnetic field. If it intersects Earth, the collision with the magnetosphere creates storms that ripple across our planet's space environment. The magnetosphere usually shields Earth effectively. Charged particles are diverted along magnetic lines toward the poles. The result is auroras that shimmer in the night sky. But during strong storms, the influx of energy can distort the magnetic field dramatically. Currents induced in the upper atmosphere push and pull the natural shield. Satellites feel the drag of a thickened atmosphere. High-frequency communication is disrupted. Dense flows of charged particles cause electronics to misfire. Power systems on the ground pick up currents that were never meant to exist. The most famous example of such a storm occurred in the 19th century. Telegraph wires sparked. Receivers hummed with currents they did not ask for. Operators reported shocks. The aurora lit skies far from the poles. If an event of similar strength occurred today, the technological consequences would be far more serious. We now rely on networks that extend around the planet. Satellites maintain communication, navigation, and timing systems. Electrical grids stretch across continents. Information moves through cables that depend on precise signals. A strong CME could disrupt all of these. This risk does not mean panic. It means awareness. The storms arise from processes that are natural outcomes of the sun's structure. Magnetic fields emerge from the interior where plasma moves constantly. The convection zone drives this motion, pushing heat outward and dragging magnetic lines along. At the surface, these lines emerge in pairs, forming sunspots. Each sunspot marks a region of strong magnetic activity. The more sunspots appear, the more likely storms become. When the magnetic fields in these regions twist too tightly, they break. The energy stored within them is released. That release is the source of storms. Consider how sunspots form. The rotation of the sun is not uniform. The equator rotates faster than the poles. This differential rotation stretches magnetic fields over time. They wrap around the star like threads drawn too tight. The fields eventually become buoyant, rising through the convection zone. When they break the surface, they emerge as dark patches because the magnetic pressure reduces convection locally. The darkness is not due to absence of heat, but relative coolness compared to surrounding regions. These patches are signs of tension building beneath. The number of sunspots varies over an 11-year cycle. During peaks, storms are more frequent. During low periods, the sun appears calm, with few disturbances. Yet even in quiet years, the potential for sudden events remains. Small magnetic regions can still form. Localized reorganizations can still occur. The cycle acts as a broad rhythm, shaping probabilities, but not controlling every detail. Earth's experience depends on the alignment of events with our orbit and the direction of ejections. At the surface, magnetic loops rise to impressive heights. They glow in extreme ultraviolet images, arching across regions of opposite polarity. When these loops collapse, they launch waves across the sun's atmosphere. The corona responds with turbulence. Shocks travel outward. Particles gain energy. Some escape along open magnetic lines, forming streams of high-speed solar wind. These streams buffet Earth with varying pressure. Even when no major flare or CME occurs, changes in wind speed can create minor geomagnetic activity. The solar wind itself is a continuous outflow of particles. It fills the entire solar system with a tenuous plasma. Earth always sits inside this flow. The boundary between the wind and our magnetic field forms a structure that changes shape with conditions. When the wind intensifies, the boundary compresses. When conditions soften, it expands. This breathing motion influences the space environment around Earth. Satellites in certain orbits may experience drag during heightened activity, leading to adjustments in trajectory. You can imagine the sun as a giant engine producing weather. Not weather in the terrestrial sense of clouds and storms, but weather in the form of charged particles and magnetic fluctuations. This solar weather is invisible to the human eye, but has consequences for technology. It can shift the orientation of satellite orbits. It can alter the clarity of GPS signals. It can degrade spacecraft electronics. It can cause currents in pipelines. It can disrupt power grids. It can shape conditions for astronauts. This becomes especially relevant as humanity explores beyond Earth. Missions to the Moon, Mars, or other regions of space must consider the threat of storms. Astronauts are vulnerable to radiation during strong events. Spacecraft require shielding. Mission planners monitor the sun constantly. A large CME could force astronauts to seek shelter within protective areas of their spacecraft. In deep space, far from Earth's magnetosphere, the danger increases. The calm appearance of the sun hides risks that must be managed carefully. Solar storms are not evenly distributed. Some erupt with little warning. Others give subtle signs. When magnetic regions grow in complexity, when loops twist tightly, when nearby areas merge, the likelihood of storms increases. Instruments detect changes in magnetic field strength. They record rising energy in the corona. Despite advances, predicting the exact timing of a flare remains difficult. The sun's surface is too complex. Small changes can cascade into large events. One might wonder why such storms exist at all. The answer lies in the sun's layered structure. The core produces energy. The radiative zone spreads it. The convection zone transports it. At the surface, hot plasma is in constant motion. These motions drag magnetic fields, coiling them. The entire system acts like a fluid dynamo. This dynamo generates complex magnetic patterns that shift with the star's rotation and internal flows. Storms are expressions of these patterns. The consequences of storms reach far beyond the sun. They shape the outer boundaries of the heliosphere, the vast bubble carved into interstellar space by solar wind. When the wind intensifies, the heliosphere expands slightly. When it weakens, interstellar particles can penetrate more deeply. Although Earth feels little direct impact from these distant boundaries, cosmic rays that enter the heliosphere can influence the radiation environment. Some research suggests that solar activity may influence long-term climate trends by modulating cosmic ray flux. The connections are subtle, but they highlight the far-reaching influence of the sun's storms. When strong events strike, we witness the power of the sun in ways usually hidden. Auroras brighten, satellites struggle, communication networks falter, engineers respond to sudden disturbances. Each event reminds us that our technological civilization is more vulnerable than we often admit. The The sun does not aim its storms at Earth. They are natural expressions of its internal dynamics. Yet our reliance on delicate systems means that even small events can ripple through society. To appreciate the scale of these storms, imagine the corona as a vast sea of charged particles. Magnetic waves rise and fall across its surface. When a flare erupts, it sends ripples through this sea. When a CME launches, it is like a tidal wave sweeping across the solar system. Earth is only one place in that system. Other planets feel the storms differently. Mars, with its thin atmosphere and weak magnetic field, experiences direct impacts that strip gas from its atmosphere. Mercury, with little protection, faces fierce bombardment. The storms are part of a system shaped by the sun's influence. What makes these storms significant is not only their power, but their origin. They emerge from the same heat and pressure gradients that keep the sun balanced. They arise from the same magnetic fields that structure the solar atmosphere. They are connected to the same convection patterns that transport energy. The sun's storms are not separate from its calm nature. They are expressions of the star's identity. Understanding them helps us see the star more clearly. We see that calm and chaos coexist. We see that the sun's surface is a dynamic field shaped by deeper forces. We see that the gentle light we rely on is part of a system that can shift dramatically without changing its outward appearance. And we see that Earth, with all its complexity, lives in the path of these events. The more we measure, the better we can prepare. Instruments monitor magnetic fields continuously. Spacecraft detect changes in the solar wind. Data streams guide forecasts. Engineers design systems to withstand storms, but predicting the largest events remains a challenge. The sun's internal complexity resists easy models. Its surface is too intricate. Its processes are too intertwined. The next chapter will follow these storms back to their broader cycle, the slow heartbeat of the sun that shapes when storms rise and fall. The sun keeps time in ways no mechanical clock can match. Its surface does not tick. Its light does not pulse at regular intervals. Yet deep within its structure runs a rhythm, a slow oscillation of magnetism and motion that shapes the conditions of the entire solar system. This rhythm forms the solar cycle, an approximately 11-year pattern in which magnetic fields strengthen, twist, collapse, and re-emerge in altered form. To someone on Earth, the sun looks unchanged across this cycle, but instruments reveal the truth. The star moves through seasons that are invisible to human eyes, yet potent enough to influence climate histories, technological stability, and the long-term behavior of space around Earth. The cycle begins quietly. Sunspots are few. The solar wind flows at moderate speed. Magnetic fields at the poles are relatively unbroken. This phase is the solar minimum, a season of comparative calm. But beneath the surface, plasma continues to churn. The differential rotation of the sun, with the equator spinning faster than the poles, stretches magnetic fields. As these fields elongate and twist, they destabilize. They begin to migrate toward the surface. Their emergence marks the start of a transition toward a more active phase. As magnetic fields rise through the convection zone, they appear on the surface as sunspot pairs. These spots follow patterns that drift in latitude over the course of the cycle. Early in a new cycle, they emerge at higher latitudes. As the cycle progresses, they appear closer to the equator. This drift creates a butterfly-like pattern when sunspot locations are charted over time. It is one of the most familiar signatures of the solar clock. Each wing of this pattern records the tension between interior flows and magnetic emergence. The butterfly diagram is a visual imprint of the sun's inner rotation. With more sunspots come more frequent storms. Flares erupt as magnetic loops collapse. Coronal mass ejections become more common. High-speed streams from coronal holes sweep through the solar system. The quiet sun of the early cycle becomes a stormy sun. And with this shift come consequences for Earth. During heightened activity, satellites face increased drag. Radiation doses rise for spacecraft outside Earth's protective atmosphere. Communication systems experience interference. Electrical grids operate under elevated stress. The star enters a season where its influence becomes more immediate. The solar cycle also includes a phenomenon known as magnetic reversal. Near the peak of activity, the sun's polar fields weaken and then reverse sign. North becomes south. South becomes north. The reversal does not happen instantly. It unfolds over months. During this time, the sun's magnetic structure becomes tangled and chaotic. After the reversal completes, the new polarity strengthens, marking the descent toward the next minimum. The reversal is a fundamental part of the solar clock. It is evidence of the dynamo mechanism that generates the sun's magnetic field. This dynamo relies on two primary ingredients. The first is differential rotation, which stretches magnetic lines into spirals. The second is the turbulent convection in the outer layers, which twists and folds the fields. The interaction between these motions regenerates the magnetic field. It is not a perfect cycle. It has irregularities. Some cycles have high peaks. Others are weak. Some last longer than 11 years. Some finish early. But despite irregularities, the sun never stops cycling. It never enters true stasis. One of the most intriguing periods in the solar cycle record is the Maunder minimum, a span in the 17th century during which sunspots became extremely rare. Historical records suggest that the sun remained unusually quiet for decades. At the same time, parts of Earth experienced colder conditions. Winters intensified. Glaciers advanced. While the link between solar activity and climate is complex and influenced by many factors, the overlap between a quiet sun and cooler periods raises questions about the broader role of solar variability. The sun's seasons may be subtle, but they are part of the long story of Earth's environment. The solar cycle also influences the heliosphere, the vast bubble carved into space by the solar wind. During high activity, the heliosphere expands slightly, pushing against the interstellar medium. During low activity, it contracts. These changes alter the flux of cosmic rays reaching Earth. When the sun is active, its enhanced solar wind shields the inner solar system more effectively from cosmic rays. When the sun is quiet, more cosmic rays penetrate. This shift affects radiation levels in space and may contribute to subtle atmospheric changes over long periods. From the perspective of technology, the cycle matters because it affects risk. During solar maximum, the probability of encountering a major storm increases. A flare that might be insignificant during quiet times can have amplified effects when the sun is already unstable. Engineers track cycle progression to prepare for heightened vulnerability. Some satellites are placed in safe modes during predicted periods of elevated activity. Grid operators monitor geomagnetic conditions closely. Our world moves in step with a star whose seasons we cannot avoid. Consider how these seasons appear through modern instruments. Telescopes tuned to ultraviolet light reveal patterns that brighten and fade with the cycle. Coronal holes, regions of open magnetic field lines, widen during the descending phase, releasing high-speed streams that buffet Earth. Infrared measurements track faint changes in brightness. Radio instruments detect bursts of emission tied to magnetic events. Each dataset becomes a dial on the solar clock, marking progression through the cycle. What we call solar maximum is not a single moment. It is a plateau of elevated activity. During this plateau, storms occur more frequently, and the sun's atmosphere becomes more dynamic. Loops of magnetic plasma tower over the surface. Waves propagate through the corona. Filaments stretch across great distances, held aloft by magnetic tension. Some of these filaments become unstable and erupt. These eruptions accelerate particles to high energies. They also seed the solar wind with structures that can interact with planetary magnetospheres in complex ways. Even with centuries of observation, predicting the exact intensity of a cycle remains difficult. Some cycles surge unexpectedly. Others remain mild. Scientists attempt to forecast cycles by studying precursor signals, such as the strength of polar magnetic fields near minimum. Stronger polar fields tend to precede more active cycles. Weaker fields often foreshadow quiet ones, but the system remains sensitive to conditions deep inside the sun that are beyond direct observation. The convection zone is turbulent. Magnetic fields thread through it in patterns that shift unpredictably. These hidden motions act like gears in a clock we can only partially see. The implications stretch beyond present eras. Over geological time, the average level of solar activity may drift. Some theories propose long-term cycles modulated by deeper flows within the solar interior. While the evidence is suggestive, not conclusive, it suggests that the solar clock may have layers of rhythm that extend across millennia. If true, Earth's climate history may bear fingerprints of solar variability that we have only begun to decode. The cycle also shapes the outer boundary of the heliosphere. When the sun's activity changes, the strength of the solar wind at great distances adjusts accordingly. These changes influence how the heliosphere interacts with incoming interstellar material. The boundary becomes more or less permeable. In regions where the heliosphere compresses, cosmic rays may infiltrate more easily. This, in turn, affects radiation exposure for future deep space missions. Understanding the solar cycle is essential not just for Earth, but for any journey beyond its protective shield. Although the cycle is usually described as 11 years, the full magnetic cycle spans 22 years. This longer cycle includes the reversal of the magnetic poles and the return to the original polarity. It is a reminder that the solar clock has multiple hands. Some mark short rhythms of months and years, others sweep across decades. These rhythms overlap to shape the sun's behavior. They influence when storms rise, when calm prevails, and when transitions occur. What does a dangerous season look like on the sun? It looks like a surface crowded with complex magnetic regions. It looks like a corona laced with loops that strain under tension. It looks like flares erupting in bursts that brighten entire regions. It looks like CMEs being hurled into the solar system at high speed. It looks like radio bursts that ripple across interplanetary space. These events can occur at any time, but they cluster around the peak of the cycle. The dangerous seasons are those when magnetic fields are tangled most tightly. The solar cycle teaches a lesson about living near a star. It teaches that even the most stable appearing light source has moods. It teaches that cycles of activity shape both local and distant environments. It teaches that understanding these cycles is essential for both technological resilience and future exploration. It teaches that the sun's surface is a map of internal processes unfolding over vast timescales. As we move forward, the next chapter will widen our view to include the influence of passing stars, the subtle gravitational encounters that may alter the orbits within our system. The solar system feels self-contained. The planets orbit in orderly paths. The sun sits at the center, heavy enough to command every world. Space appears empty. Distances between stars seem so vast that nothing outside our system should matter. Yet this impression of isolation is misleading. The sun is not fixed. It drifts through the Milky Way in a long circuit that carries it through regions of varying stellar density. Other stars move too, each tracing its own path. Over millions and billions of years, these paths intersect. Stars approach one another. They pass in the dark. Their gravity extends far beyond their visible light, and even a distant encounter can change the architecture of planetary orbits. To imagine such an encounter, picture the solar system as an island floating in a wide ocean. From coastlines, the water looks still, but beneath the surface, currents shift. They tug at the island from directions that seem impossible to detect. A passing star is like an underwater current. It may not strike the island directly, yet it can still reshape the environment. The solar system is not a rigid clockwork. It is a delicate balance of gravitational relationships. When another star drifts close, that balance shivers. The distances involved are large, but gravity can reach across them. If another star approaches within a few light years, its pull affects comets in the distant Oort cloud. These comets orbit the sun loosely. They form a vast reservoir of icy bodies, extending almost halfway to the nearest star. A passing star can perturb the outer regions of this cloud, sending comets inward. Over long time spans, such encounters may contribute to bursts of comet activity. In extreme cases, the orbits of planets may also shift. The amount of shift depends on the mass of the intruding star, the distance of closest approach, and the timing of the encounter. Such events are rare in human terms, unfolding on scales that dwarf recorded history. But the galaxy is old. Billions of years provide many opportunities for chance alignments. Some simulations suggest that within a few billion years, other stars may pass close enough to alter planetary orbits. These changes need not be dramatic. A slight shift in Earth's orbit could alter climate patterns. A more substantial change could disrupt the stability of the inner planets. Small differences in orbital spacing can accumulate into larger consequences through gravitational resonance. Over millions of years, even modest perturbations may become significant. One might imagine these encounters as violent collisions, but most are quiet. They resemble a faint pull rather than a blow. The intruding star does not tear planets from their orbits. It nudges them. It disturbs the equilibrium. In some cases, the intruder may be a dim red dwarf, nearly invisible to the naked eye. In others, it may be a larger star. The Sun itself will pass near other stellar systems during its long journey around the galaxy. Each pass alters the orbits of distant objects over sufficient timescales. These cumulative effects shape the outer architecture of the solar system. This perspective reveals a deeper truth. The solar system is part of a network of gravitational interactions. It is not an isolated arena. It belongs to a sea of moving masses. The galaxy is crowded. Even if the distances between objects appear vast, stars drift in and out of regions with different densities of gas and dust. They pass through spiral arms. They interact with clusters of older stars. These encounters influence the orbits of planets, comets, and asteroids. Perhaps the most striking aspect of this dynamic is how little we notice in the short term. Human lifetimes are too brief to detect these shifts directly. The motions are too slow. The gravitational influence of a passing star might unfold over tens of thousands of years. Yet such encounters have long-term consequences. They may help explain irregularities in the distribution of comets. They may influence the stability of planetary orbits. They may alter the boundaries of the heliosphere, the region shielded by the solar wind. To understand the significance of these encounters, consider the heliosphere as a vast bubble blown into space by the solar wind. Its shape changes with solar activity. During quiet periods, it contracts slightly. During active periods, it expands. A passing star, with its own stellar wind and magnetic field, could distort this bubble. If the encounter is close enough, the boundary between the solar wind and the interstellar medium may shift dramatically. This shift could expose the inner solar system to higher levels of cosmic radiation. The encounter would not be catastrophic, but it would change conditions for any future observers living on planets or spacecraft. The gravitational influence of a passing star can also affect the orbits of planets indirectly. Even if the encounter is not close enough to disturb Earth directly, it could perturb the orbits of outer planets slightly. These perturbations could propagate inward over time through resonances. A small change in the orbit of a giant planet like Jupiter can lead to cascading effects. The inner planets sit in gravitational relationships that are sensitive to long-term shifts. A slight alteration in orbital parameters could influence Earth's climate or even its long-term stability. Some models suggest a small but non-zero probability that Earth's orbit could become more eccentric or be displaced in rare scenarios involving close encounters. The solar system has survived many such encounters already. Over 4.5 billion years, the Sun has passed near regions of higher stellar density. It has drifted through the galaxy's spiral arms. It has crossed the plane of the Milky Way repeatedly. Each crossing likely increased the rate of cometary perturbations. Each pass near star-forming regions may have brought the Sun into proximity with newborn stars. The current calm is not a permanent state. It is a moment in a long motion through a complex environment. This understanding reshapes our view of stability. The planets feel secure in their paths around the sun. The sun itself seems a fixed anchor, yet on long timescales, the anchor drifts. It drifts in a sea of other anchors, each tugging on the others, over billions of years. The architecture of planetary orbits becomes a record of these encounters. Slight irregularities we observe today may be echoes of events long past. In this sense, the solar system carries memory in the form of orbital configuration. These encounters also shape the story of habitability. Earth thrives because its orbit remains relatively stable. Too much eccentricity could lead to extreme temperature swings. Too little distance from the sun could trigger runaway heating. A passing star could theoretically shift Earth's orbit subtly. Even a small change, accumulated over time, might influence climate. While such outcomes are statistically rare, they remind us that habitability depends not only on the internal processes of the sun, but also on the gravitational environment of the galaxy. Looking ahead, future encounters are possible. Over billions of years, stars that are currently far away may drift closer. Some may approach within a few light years. Others may pass within hundreds of astronomical units. These distances are vast, yet the gravitational effect remains real. The solar system's distant boundaries would feel these effects first. Comets may be nudged inward. Planetary orbits may shift slightly. The heliosphere may change shape. Each encounter becomes part of a larger tapestry that extends across cosmic timescales. To see the significance of these events for civilization, imagine a distant future in which humanity, or its successors, travel through space. Spacecraft may need to navigate changing cosmic ray environments. Colonies on outer planets or moons may experience altered radiation levels. Missions to interstellar destinations may rely on precise models of the heliosphere's boundaries. Understanding these encounters becomes essential for long-term planning. The galaxy is not static, and neither is our place within it. The most profound implication lies in how these encounters interact with the sun's own evolution. As the sun ages and approaches its red giant phase, the influence of passing stars may alter its planetary environment further. A slight shift in Earth's orbit could determine whether it is engulfed or scorched from a distance, while the sun's expansion ultimately seals Earth's fate. Encounters with other stars may shape the details of that ending. Even now, scientists track nearby stars with precision. Some stars are predicted to pass close to the solar system in the distant future. Data on their trajectories helps refine models of how often such encounters occur. These projections are not warnings. They are part of the broader story of how the solar system interacts with its galactic surroundings. The calm sky above Earth hides these slow motions, yet they are always present. The solar system's long-term fate is not determined by the sun alone. It is shaped by the gravitational interactions of countless stars moving in concert. The galaxy breathes. The stars drift. The solar system moves with them, and as it moves, encounters accumulate. Each encounter adds a subtle thread to the tapestry of planetary motion. From this perspective, Earth's orbit is not a fixed path but a temporary pattern in a dynamic universe. The next chapter will reveal how new instruments sharpen our view of the sun's restless surface, offering clarity about the forces driving these long-term changes. The sun once seemed unknowable. Its brilliance hid its details. Its surface appeared smooth, its edges soft, its glow uniform. For most of human history, no one could see beneath that brightness. The star looked like a flawless disk, a perfect sphere of light without structure. Only in rare moments, during eclipses, did hints of complexity emerge. Now, with new instruments that peer through wavelengths invisible to the eye, the sun has become a world of motion, texture, and hidden architecture. Its surface is restless. Its patterns shift from moment to moment, and the closer we look, the stranger it becomes. Modern solar telescopes reveal structures no wider than a few dozen kilometers, features so delicate that previous generations could not have imagined them. These narrow threads of magnetic energy twist above the surface like strands of woven metal, They are not static. They move, dissolve, reform, and sometimes snap. Each thread carries heat and motion into the upper layers. When thousands of such structures interact, the sun's atmosphere responds in waves and pulses. The fine-scale terrain of the sun, once invisible, now appears as a textured landscape shaped by forces deeper than sight. Consider the convection cells visible beneath the surface layer. They rise and fall continuously. Each cell is a parcel of plasma heated from below, lifting toward the surface where it cools and sinks again. High-resolution imagery shows that these cells have intricate edges. Thin filaments of bright plasma outline their boundaries. Dark lanes mark regions where cooler material descends. The pattern resembles a mosaic in perpetual motion. As new instruments sharpen their view, they reveal subcells within cells, patterns within patterns. The sun's motions occur at every scale, from large sweeping flows to tiny jets of plasma only a few kilometers wide. The corona, the sun's outer atmosphere, becomes even stranger under sharper observation. Temperatures in the corona are far higher than those at the visible surface. This inversion has puzzled scientists for decades. Something must transport energy upward from the lower layers, heating the corona without relying on direct contact. High-resolution imaging suggests that small-scale magnetic motions contribute to this heating. Jets of plasma, sometimes called spicules, rise from the surface continuously. They carry mass and energy upward. When observed in detail, they appear and vanish rapidly, as if flickering between states. Magnetic braiding has emerged as a strong candidate for coronal heating. In some regions, magnetic fields twist around one another. The tension created by this twisting stores energy. When the fields snap into a simpler arrangement, energy releases suddenly, producing heat and waves that propagate through the corona. Previous instruments could only observe large-scale eruptions. New telescopes, equipped with adaptive optics and specialized filters, can detect the smaller events that happen constantly. These events may not be dramatic individually, but combined they could explain the corona's extraordinary temperature. The sun's surface also contains bright points, small localized bursts of energy that appear without warning. These points often form at intersections of magnetic fields. They shine intensely for seconds or minutes, then fade. High-resolution imagery reveals their complexity. Some consist of swirling plasma, others erupt upward in thin jets. Their frequency increases in areas of strong magnetic activity. Their presence suggests that the sun's surface is far from uniform. It is a patchwork of interacting flows and fields that constantly rearrange themselves. To observe these features, telescopes must overcome intense heat and turbulence. Instruments at ground-based observatories use mirrors cooled by elaborate systems. They employ adaptive optics to compensate for distortions in Earth's atmosphere. Space-based telescopes avoid these distortions entirely. They float above the atmosphere, capturing images with unprecedented clarity. Filters isolate specific wavelengths corresponding to layers of the solar atmosphere. When these images are combined, they form a three-dimensional view of a surface once considered flat. The sharpened view reveals something unexpected. The sun's smallest structures may play a large role in shaping its behavior. Magnetic fields that appear insignificant at coarse resolution become important when examined more closely. They cluster in patterns that act as seeds for larger events. They influence how energy flows across the surface. They help determine where storms originate. They shape the corona's structure. The sun's activity cannot be understood solely by studying large features. It is the cumulative effect of countless small structures that matters. This discovery changes our understanding of the solar cycle. Sunspots, long used as indicators of solar activity, are only one part of the picture. Magnetic fields rise to the surface in many forms, not all of which produce spots. Some form small pores. Others emerge as faint, short-lived features detectable only with sensitive instruments. These subtle signs of magnetic emergence help researchers track the evolution of the cycle. They reveal how the interior dynamo leaves its imprint on the surface. Sharper eyes also expose the true nature of flares. A flare begins in a region of magnetic complexity. High-resolution observations show that the initial spark of a flare can occur on scales far smaller than previously recognized. A tiny reconnection event can propagate outward, triggering larger changes. This progression resembles a chain reaction. One small event destabilizes nearby loops. Those loops collapse and heat rapidly. The flare grows into a large eruption. The initial cause is lost in the brightness of the event, but sharpened imagery helps trace the spark. The insights gained from high-resolution observations also influence how we prepare for solar storms. Spacecraft designers must plan for radiation conditions. Grid operators must anticipate geomagnetic events. Astronauts rely on warnings when solar activity rises. The ability to detect small-scale changes improves forecasts. It allows earlier detection of magnetic complexity. It helps determine when regions on the Sun are becoming unstable. Although prediction remains difficult, sharper imagery closes the gap between early signs and visible eruptions. Such observations also illuminate the long-term evolution of the Sun. By tracking small features across many years, researchers can identify patterns that reveal how magnetic fields drift and change direction. These patterns are tied to the solar cycle's phases. They help refine models of the dynamo. They offer clues to how the Sun's internal flows change over time. In this sense, high-resolution observations act as a window into the deeper workings of the star. There is an aesthetic dimension to these discoveries as well. The Sun's surface, when viewed at high resolution, no longer resembles a smooth disk. It resembles a living tapestry woven from light and magnetic filaments. Bright loops rise and fall. Plasma flows outward in waves. Dark lanes shift. Tiny bursts of energy appear and vanish. The star that once looked simple reveals itself as a world filled with motion and detail. This transformation of perception deepens the sense of connection to our star. Sharper imagery also influences our view of future risks. Small-scale structures may indicate where the next flare will originate. They may offer clues to the likelihood of a strong CME. They may help identify times when the corona is unstable. Even subtle changes in the shape of loops or the brightness of certain regions could indicate larger events to come. With each improvement in resolution, our ability to interpret these signs grows. The Sun's surface also changes with latitude. Near the poles, magnetic features behave differently than near the equator. Polar crowns of plasma shift location. Waves of activity migrate from mid-latitudes toward the equator as the cycle progresses. High-resolution instruments track these movements. They reveal how polar magnetic fields contribute to the cycle's progression. These fields play a key role in the reversal that occurs at solar maximum. Understanding them requires detailed measurement at scales that only modern instruments can achieve. It becomes clear that the Sun must be studied at every scale. Large features reveal global behavior. Small features reveal local dynamics. Together, they form a complete picture. Without the fine details, our understanding would remain shallow. Without the large structures, the fine details would lack context. The new generation of solar telescopes unites these perspectives. They allow us to study the Sun as both a vast engine and a detailed landscape. This chapter has shown how sharper observations reveal the true complexity of the Sun. It is not a smooth sphere, but a realm of motion and change. Its surface hides patterns that only careful observation can uncover. Its smallest features influence its largest events. Its restlessness becomes clear when viewed through instruments that capture the finest details. And these insights guide us toward a deeper understanding of the Sun's future. The next chapter will carry us into that future, following the Sun as it enters the final phases that reshape the fate of every world in its orbit. The Sun does not die in a single moment. Its ending unfolds slowly, like a long-held breath released over ages. The first signs appear deep in the core, where helium ash accumulates. Hydrogen burns in a shell surrounding that dense region. As the core contracts under its own weight, pressure and temperature rise. These changes alter the star's balance. The outer layers respond by expanding, The sun brightens. Its color drifts from familiar gold toward a deeper hue. None of this is sudden. None of it announces itself loudly. Yet each step marks progress toward an ending that every planet must eventually face. Earth's fate is tied to this sequence. As the sun brightens, the habitable zone moves outward. Oceans warm. Evaporation increases. Water molecules drift higher into the atmosphere, where ultraviolet radiation breaks them apart. Hydrogen escapes into space. Once this escape accelerates, it becomes difficult for a planet to retain liquid water. Long before the sun reaches its red giant phase, Earth will face heat that reshapes its surface. This transformation is not violent, but persistent. Landscapes dry. Weather patterns shift. The blue planet becomes a world of shrinking reservoirs and rising temperatures. As the core continues to contract, the hydrogen-burning shell moves outward. The outer layers expand further. The sun grows large enough that its surface cools. Seen from afar, it becomes a giant star with a reddish tint. The diameter increases by a factor of many tens. Mercury and Venus feel this growth first. Their orbits place them close to the expanding star. Their surfaces, already extreme in their conditions, become engulfed or stripped. The sun's outer atmosphere reaches toward them. They lose the last traces of their individuality. The sun's growth erases their boundaries. Earth stands farther out. Whether it is engulfed or scorched depends on details that remain uncertain. Orbital shifts caused by the loss of solar mass during expansion may place Earth at a slightly greater distance. Some models suggest that Earth may escape direct engulfment. Others suggest the pull from the swollen atmosphere could drag Earth inward, even if Earth remains outside the sun's physical radius. The heat pouring from the expanded star will strip its atmosphere and melt its surface. The planet becomes a barren sphere, glowing faintly under the giant star's light. The solar wind changes as the sun expands. It grows stronger, carrying material outward in a steady flow. This wind strips the atmospheres of outer planets too. Mars, already fragile, loses the little it has left. Gas giants may experience changes in their upper layers. Moons that once harbored subsurface oceans face rising radiation and shifting gravitational forces. The entire solar system feels the star's transformation. Orbits shift slightly as the sun loses mass. Comets in the outer regions follow altered paths. The architecture of the system evolves. At some point, the core reaches a temperature where helium ignites. This ignition is sudden on stellar scales. The core stabilizes briefly, and the sun settles into a new balance. It burns helium into carbon and oxygen. This stage provides a momentary calm, but it cannot last. Helium fuel runs out more quickly than hydrogen. Once the helium is gone, the core contracts again. The outer layers swell once more. Pulsations begin. The star sheds material in expanding shells. These shells drift outward in waves of glowing gas. The star that once nurtured life becomes a giant shedding its outer layers. Those layers form a structure of expanding rings and filaments. The exposed core, now extremely hot, illuminates the material drifting away. The result is a planetary nebula, a glowing cloud shaped by the star's final breath. Colors spread across space. Patterns emerge from the interactions of stellar winds and ejected layers. From a distance, the nebula becomes a brief jewel in the darkness. The core that remains is a white dwarf. It contains the sun's remaining mass compressed into an object roughly the size of Earth. Its gravity is immense. Its temperature is high. It shines with residual heat, gradually cooling over billions of years. The story of the sun ends with this faint glow. The planetary system that once orbited around it becomes a remnant of scattered objects and altered paths. Some planets may survive as cold spheres. Others may be destroyed. The white dwarf becomes a monument to the star's long history. From the vantage of deep time, this ending is common. Many stars follow similar paths. The sun is not unusual. It is part of a sequence written into the laws of physics. Its transformation reflects the balance between fusion and gravity, between heat and structure, between creation and decay. But for Earth and any beings that may arise within its history, this ending is personal. It marks the conclusion of a planetary story that began with the first pools of liquid water and the earliest stirring of life. What remains after the sun's transformation is a system reshaped beyond recognition. The nebula fades after tens of thousands of years. The white dwarf cools. The memory of the sun's earlier brilliance persists only in the elements scattered throughout space. These elements may drift into clouds that later form new stars and planets. In this way, the sun contributes to future worlds. Its ending becomes part of the beginning for others. If an observer in a distant future looks upon the remnant of our star, they may see only a faint dot of light where a giant once rose. They may find no trace of Earth. Yet the atoms that filled Earth's oceans and mountains will continue their journey. They will travel across interstellar space, waiting to become part of another planet, another surface, another story. The sun's final act becomes a bridge between worlds separated by time. The next act will turn from these stellar transformations to the meaning they carry for beings capable of reflection, beings who must consider their place in a universe where even stars must fade. When the sun finally swells beyond recognition, when its last storms fade into drifting shells of color, a quiet truth settles over what remains. Stars are temporary. Their warmth is temporary. Their stability, their cycles, their tender balance between gravity and fusion, all unfold along a timeline far longer than the lifespans of civilizations yet still finite. And when the light begins to thin, the memory of a world that once circled the sun becomes its final legacy. This act is not about the physics of that ending, but the meaning carried within it. To see the sun in its late state is to watch a story unspool across deep time. The white dwarf at the center of a fading nebula is only a shadow of what the star once was. The sun that lifted Earth's oceans and coaxed forests from rock. The sun that warmed early life and illuminated every generation that ever lived becomes a single point of light. Its brilliance no longer rises each morning. It no longer defines the rhythm of days. It simply cools across eons, shedding its heat into the night between stars. Yet its influence persists. Every atom of carbon in a leaf, every grain of calcium in bone, every drop of water that once flowed through rivers, was shaped by the processes that unfolded during the sun's long main sequence life. A star creates the conditions for planets, but does not decide how life uses those conditions. The relationship between Earth and the sun was never a simple link. It was an ongoing conversation between energy, chemistry, and time. Life responded to each shift in the sun's brightness, to each long season of calm or storm, to each cycle that left subtle imprints on climate. The sun may now be silent, but its influence extends through the matter it once illuminated. The philosophical echo deepens when you consider that stars do not end alone. Their endings feed the beginnings of others. A planetary nebula may disperse over tens of thousands of years, but the atoms it contains drift outward. They mix with interstellar gas. They become part of future star-forming regions. In this sense, the death of a star is a contribution to the galaxy. Every white dwarf marks a chapter that has been closed, but every cloud of expelled material becomes part of chapters still unwritten. There is a symmetry in this. The sun itself was formed from the remains of earlier stars. Its hydrogen and helium date back to the early universe, but its heavier elements were forged in more ancient furnaces that lived and died long before the solar system existed. Earth is built from these remnants. Life arose on a world composed of recycled stardust. And someday, long after the sun's nebula fades, the elements that built Earth will disperse, waiting to join another world around another star. This continuity suggests that planetary stories never truly end. They change form. A star's life can be read as a reminder of impermanence. We often treat stability as a default state. We imagine that the sun's warmth is a permanent backdrop for human concerns. But permanence is an illusion born of short lives. In the cosmic scale, everything is motion, everything is transition. The sun's quiet glow, which seems so steady, is only a phase. Its final expansion, its shedding of layers, its slow cooling, are all natural expressions of a long arc governed by known laws. Yet impermanence is not the entire lesson. The sun's life cycle also reveals a form of generosity. A star does not merely shine, it shapes, it builds, it provides the conditions for complexity. The energies that will one day unmake Earth are the same energies that made life possible. The long era of habitability, the presence of liquid water, the cycles of climate, and even the stability of chemistry, all emerge from the sun's long, burning core. The ending cannot be separated from the beginning. The story is unified. For beings capable of reflection, this raises a deeper question about place and purpose. If the world that nurtured us is temporary, what responsibilities arise from that knowledge? If the sun's future guarantees an eventual transformation, does this compel its observers to look beyond Earth for continuation? Or does it invite them to understand their home more fully? Knowing that its existence is a finite gift, civilizations may grow in the shadow of a star, but they do not have to remain there. The sun's ending is not a threat. It is an invitation to imagine futures that extend beyond the boundaries of its warmth. This perspective casts a new light on exploration. Every measurement of the sun, every prediction of its changes, every mission sent to study its surface, becomes part of a long-term effort to understand the environment that shaped us. The more we learn, the clearer the path becomes. Knowledge becomes preparation. Understanding becomes resilience. The awareness that the sun will change encourages the building of technologies that reach further. It encourages new forms of shelter, new ways to travel, new ideas about how life might continue beyond a single star. There is an emotional dimension too. To know the sun's fate is to confront the finite nature of familiar things. The sunrise, the seasons, the shifting warmth across a landscape are not universal constants. They are features of a specific moment in cosmic time. A star's final act transforms those familiar experiences into memories. For anyone who contemplates such an ending, the question becomes more personal. What makes a world meaningful if its foundation is destined to dissolve? Meaning does not arise from permanence. It arises from participation. Earth existed for billions of years without observers. It held oceans and mountains long before consciousness appeared. But once observers emerged, the relationship changed. The sun no longer simply illuminated a planet. It illuminated minds that could understand the light. The story of the sun became intertwined with the story of life that looked back at it. Even when the star fades, the record of that relationship persists in the matter left behind, and in any beings who carry the memory forward. Reflecting on the sun's ending also reveals the importance of perspective. From Earth, the sun seems enormous and eternal. From the scale of galaxies, it is one among hundreds of billions, each following its own arc of birth, stability, and decline. The processes that govern our star are universal. Other civilizations, if they exist, may watch their own suns enter giant phases. They may witness nebulae glowing in the night sky where their home once circled. They may face similar questions about continuity and meaning. The story of the sun is not unique. It is part of a broader pattern written into the physics of stars. There is a quiet beauty in this universality. The sun's life is both ordinary and extraordinary. Ordinary in its adherence to known processes, extraordinary in its ability to shape a world full of complexity. Its ending does not diminish its earlier contributions. It completes them. It returns its matter to the galaxy. It leaves behind a pattern of orbits, a cooled core, and countless atoms waiting for new possibilities. In the final view, when the nebula disperses and the white dwarf dims, the sun's story becomes an echo carried through the cosmos. The planets that orbited it may be gone or transformed. The beings that contemplated it may have vanished or moved on, but the imprint remains in the chemical trails left behind. These trails will someday seed new clouds, new stars, and perhaps new minds capable of reflection. Spectacular endings in nature often come with quiet questions. The sun's final glow invites one that has no simple answer. When the light of our star becomes only a fading ember, who or what will remember the world that once turned beneath it?